Okay. Thank you. Thank you for invitation. Thank you for being here. I feel more Tunisian now than Swedish. Very nice to be here. Thank you, Samir, for organizing here and keeping me busy, as always. Last time you said that my presentation was about more tourism. Now I want to make more technical. So I present, so it's not a lecture in precision machining, it's a presentation of our research in this field, and I will present our approach, the concept that we developed. So if you read this title, is about precision of machining systems. So I explain what I understand by machining a little bit later. So the presentation that I think to make today is about precision capability, elastically linked system and loaded double ball bar, testing of machine tools under loaded condition, modeling, and finally conclusion about the strategy for compensation for errors. So, first something that maybe everybody is familiar with, this type of representation of precision machine tools and components, elements in the machine tool. There are structural elements and there are elements connected to the control system, drivers, and so forth. And then please define the performance of machine tool with respect to some performance criteria like kinematics, dynamics, thermal errors, and so forth. So this is a quite familiar picture that I think everybody has a understanding. The problem here is that it's about the precision machine tools. And this is more interesting from the point of view of manufacturers, but for users, we are interested of this interaction between machine tool structure and elements and the machining process. So for instance, the error thermal deformation or thermal deviation can come as well from the cutting process or from the machine tool structure, friction for parts in movements. So this is the new aspect that we developed in my group. So machining system will define as interaction between machine tool structure and the control system and the cutting process. So in this interaction between these two subsystems, we'll study the precision of the system. As in any other mechanical system, structure is excited by a force, and that the output of the structure system will get some deviation, static or dynamic vibration, and this is the input in the process. And the variation at the output of machine tool structure will generate deviation in cutting condition that result in deviation of cutting force, and this can be amplified or damped down. Now, about this link between precision of machining system and accuracy. About the nomenclature, I use the traditional way, so it's everybody knows that is a difference between precision, which is connected to repeatability and accuracy. But I use the standard definition. Also, in my opinion, for point of view machine tool machining system is more important this precision feature with respect to delivering all the time the same characteristic of the part. While machine parts is well better defined them more accuracy is a static point of view. So, in machining system precision, we talk about machine structure, about precision control system. All of them contribute to the precision system. While in the machining part accuracy, we have dimensional tolerances, we have geometrical tolerances, and surface finish. There are of course, there are many other parameters that can define a part, but from point of view of accuracy, we can agree that this is sufficient. Now, machining system is also connected to machine system capability. In terms of position, kinematics, accuracy, thermal deformation, dynamic deformation, vibration, static deformation. So these are the main group of the error or deviation from accuracy that can be belonging to one or the other group. There are two methods to define the precision of machining or machining system. So one is an indirect method and belongs to quality engineering area. And that what you are doing, you are measuring the parts, so output from the system. And by this we define some index, normally called capability index. So we don't measure anything in the system, we measure the output in terms of outcomes. So the main limitation, I think that is missing one picture. Yeah, okay. Then we go to this direct method. Direct method, so it make a difference. Here we are talking the machining system because the output depends both of the machine tool and about the process. But when we are talking that current methods for evaluation through direct methods, these are referring only on the machine tool. So they are looking only capability between of machine tool outside machining process. And there are some equipment that are used today for controlling the precision. One of these is double ball bar, and other is this laser interferometer. I can show you how double ball bar in case that you don't know what about this. I can. So this is double ball bar instrument. So this first part is to calibrate the machine tool table and to calibrate the spindle position and then you fix the fixture on the table. So this is calibration. Then you bring this double ball bar, you see it's called because it's a bar and two balls here. And then, I don't know, you know about this is a quite a normal procedure. And then you execute a rotation. These bars can have different lengths and you produce a circular trajectory and you measure the deviation from a circle. And you make a counterclock and to make a rotation circle. In some machine you have both table and spindle to produce this rotation. In other, only as in this machine, only only the spindle, the tail is fixed. To produce this type. Other method which is more accurate is by laser interferometry, so triangulation, but these are not so popular in industry. Now there are two limitations of these methods. One of them is that it's this lack of holistic approach, so between the connection between machine tool, machining process, and the system, measurement system. And the other, it's so the most say limitation is that is not any connection between the part that we produce and what is the source of errors. So you measure a part with the direct, this indirect method. We know that there is some deviation from the specification, design specification, but we don't know what in the machine tool is the source of error. So for this, we have to go in deep with. So this deviation can come either from the machine tool or from process. So it's difficult to discriminate between two. So this is the major. So therefore, we develop a new method. So first, to introduce, we develop this concept which is called elastically linked system. So normally, a machine tool in off operation is in a state of open loop. So you have an open force from the tool through columns back to workpiece. Now when we start machining, then we close this loop through the tool. So we have two loops, a open loop and a closed loop. So here is the model that we developed. So you have a force loop through the elements of the machine and another loop that closes this energy loop. And this is the concept of elastically linked system. What means this? That we can simulate the effect of machining, at least at this stage, static forces and kinematics effect by changing the load between spindle and the machine tool table. And based on this concept, we developed so-called loaded double ball bar. By this concept and method, we can link directly the precision of system to machine part accuracy. We can now evaluate exactly from a certain path of the tool in the workspace of the machine, we can predict what will be the machining part under assumption that we consider some forces which are connected to some coupling parameter. So this elastic link approach consists in 4 steps. The first step is it's an off-line operation. We are loading the spindle, nose, and table with different. So the instrument, I'll show that a bit later, is similar to double bore bar, as you have seen before, but we can apply a load. So this load can be varied between 0 and approximately 800, 960 Newton. So in the first step, we are loading the double bore bar, so spindle and table, and we make the same circular trajectory that you have seen before. So what we are getting, we are not getting the error, we are getting the deformation in the system that time. So in the double bore, we get the error in kinematics and position. Here you get effects both from the deformation, so starting deformation in the machining system, and kinematics. So by connecting this closed loop. So now we find out deformation in the direction of the loading for different angles. If we extracting from this some direction of forces and deviation, we can find out the deviation with respect of a certain coordinate of system. Okay? I will come back. Then we can populate all this workspace with value of stiffnesses of deformation. So any point in space we can calculate the stiffness. We can know the stiffness and calculate the deformation, can calculate forces in any point. Then, if you have a workpiece of certain, say, form, we generate a trajectory in this space, and we find out what are the deviations on the workpiece. So, the first method that is this indirect method that is used normally in today for modeling is called bottom-up. So what means also for finding distribution of error? We start from each individual connection between two elements in relative motion that can be rotational or translational. And you make a model how the error between these two components will be. So you have a certain coordinate. So the method is called homogeneous matrix, you probably know methods. Make a matrix of all these errors that are in translation or rotation. So you build up the whole machine. So this is called bottom up because on the whole you get the budgeting of the error. So total error that you can produce. But this is a prediction because this is based on most assumption models. What we are doing here is a top-down. We know exactly the deviation in the direction of the force. We know exactly. And for this we are projecting in different coordinate system, and we find deviation in different axes. So from this, at this point we know exactly what is the deviation. We will see soon what are the limitations. So we are using here a multi-body component to calculate, evaluate in any point in space the deformation or alternatively the stiffness. So this is the system. So double bore bar, so loaded double bore is very similar to the conventional double bore, but contain an air cylinder. And we measure with the length gauge, we measure displacement and we calculate forces that we apply. So you have a table joint and a tool joint. So in we loaded this with different forces and we make some exactly as in the conventional generate some trajectory. It can be in XY plane or any plane that permit the machine tool. So we are getting for different forces, we're getting such trajectories. So each force here, each curve here represents deformation, and so it's not only deformation of the static deformation, including even kinematics and position, because you are making a movement in space. And not only this, we can also calculate from this curve even the nonlinearity in the system. And this is both kinematics and static. We cannot at this time separate what is coming from static or coming from kinematics. No? From the time is, also from point of view of users, so there are these two parts in this field. One is the user that is interested to produce an accurate part. The other is maintenance engineering, is to find out how to improve this. I can tell you later about limitations. So here's the displacement xy prime for different loads. And this is in static stiffness calculated for this curve. So you can, in any plane, we can make this type of experiments. Now, if from this we take in some direction, so we know exactly what is the force, which are the deformation. So if we take in some direction these forces, so from point of view of users, we can now configure, if we know exactly this part, we can, what is interesting for point of user is the relative displacement between tool and workpiece. So if we know this deviation, we can model with, for instance, 6 degrees of freedom, the spindle, 6 degrees of freedom. We can calculate from this system, we can calculate this one. So we don't need more in order to calculate deviation here. So from point of view of user, but for point of view of maintenance, we want to distribute this error here further in the system. So we developed also a kinematic model for this. So we can calculate, so here is the direction of this double bore bar, the force and corresponding deviation. So now we can calculate for extracting the forces in different planes. We can calculate, also distribute the error here to joints, for instance, columns, and go further to, depends here. So the disadvantage of top-down is that we know exactly what is happened here, but this we have to use some variational calculus or similar to distribute the error. So the longer we are going in system, the larger is the error. But from, as I said, from point of view of the user, it's enough to know this deviation to make a trajectory in the model and to calculate resulting forces. So we calculate such a deviation matrix for all these joints, and also the better the model, the better our prediction. So I will show you some. So this is the predicted in a certain plane. For instance, we want to make a circular trajectory, and this is the result for the calculation of different forces. So after making, so this will be the error or deviation, the workpiece. So now we can link directly the machining system precision with this deviation that we are supposed predicting on the workpiece. So we make some, to validate this method, we make some measurements. So we place this LDPP in 7 position, and we make trajectory, circular trajectory, and we calculate corresponding deviation. And then we use a coordinate measure machine to measure this deviation and compare to the result that we had. So this was the circular piece that we machined. We measured the accuracy in a coordinate machine, and we compare to the one that was produced in the model. And we are, I don't know if you can see here, the force error in calculation force are under 10%. Now this also must be a little bit considered with caution, because the force measurement itself has a quite big error range. So normally with the existing commercial system like this that we are using, you cannot measure to say accuracy repeatedly better than 15%. So this 10% must be understood in the right frame. But anyhow, the accuracy that we measure, also comparing with that we are getting from the model, it's very, the error is very small, so this is also under 10%. So next step is that now we compare these two, model and the experiment, and we make then a correction in the algorithm and in the model. Now there are two direct application of this concept. So now we know exactly the forces. We know force, we know cutting parameter, we know exactly what will be the deviation on the workpiece. Based on this, we can compensate for errors either by reducing the cutting force under the minimum force that producing this deviation, or make a more, say, dynamic strategy by changing in the program. So you can change in the MC program part. We can change the forces and corresponding the cutting parameter that correspond to the this deviation that we want to compensate. We are in this program, we are working to. So initially the project was performed together with Scania, but then this device was produced by a company that is called C.E. Johansson. Probably you know, because you're one of the older companies that developed a lot of instruments. This company was bought by a UK company, it's called Hexagon. So now this project is financed by Hexagon, so next step is to develop what I didn't mention, as in double bore bar, this bar is fixed between spindle nose and table. But the most effects in, at least from static point of view, comes from tool and or from the workpiece, if you have a quite flexible workpiece. So what we are doing in the model, we are adding in this finite element which base this multi-body, we are adding the tool and the workpiece. So these are including for, and also from our experiments, we find out the most error comes not from kinematics or position, but comes from tool deformation, or alternatively from the workpiece, also vibrational. So as soon as, for instance, increasing the tool length, you are coming in vibration, they are giving deviation much larger than we can get from the. We also saw a quite large effect coming also even from tool wear. So important is to separate these effects coming from workpiece, from the process and the machine. So right now we can link directly to the machining system to the outcomes, to the machine part. Remains to see further if we can better to predict the deformation different components, because here it's still a statically difficult to express a deviation in movable parts. So in guides, so the most error comes from movable parts, from spindle or from the guide stable screw drives and guides. So this is more difficult because are very difficult tribological problems, but we'll start to also to go in deep. Okay, this is, I think that is
Does it have to be horizontal, or it doesn't matter the orientation?
Now, this is also, now there is a problem when you have loaded, because if you want to keep constant, also what you want to keep constant is the force in loaded double bar or the force in the component, because if you have a force which is vertical, you have no component here. So they have a compensation, the system, that taking account. So in fact, you are interested about the projection in the direction, not what we have in the system. So it's compensating. Also, it's compensating for the. It's compensating also for the. Because you have a deformation even in these joints. So you have also compensation for this deformation in the joints, both stable and spindle. What you are now preparing, because most important part is the stiffness and deformation kinematics error also vary in with respect to the speed. So now I am preparing a system that permit to rotate the. In fact, also for ceramics bearing is not recommended to use such methodology, because you destroy the bearing, so it didn't apply for this. So you need a movement. But they are compensating for the loss. You can apply in any plan usually.
And
The
how you know the
horizontal,
angle?
vertical. Unfortunately, I don't have this video or this record that show how this rotate. But as this conventional double bar, you can rotate this plan. Also that machine tool permits. So if you have a 5-axis machine tool, you can also basically you can do any plan. Yes.
Est-ce qu'on peut intégrer le modèle cinématique de la machine dynamique dans la sienne afin d'optimiser les paramètres technologiques de usinage?
So dynamics we don't have at this level, and also depend on what you mean by optimization with respect to what? To the performance of the...
La compensation directe de l'erreur par la sienne de la machine.
So compensation, we can do now direct compensation in 2 ways, as I said, also, or 3 ways even. One way is to decrease the cutting parameter, which is not optimization. Another is to increase, so we have a method that it's another history that we can we can change the stiffness here. So we develop some actuators based on hydraulic and even pneumatic to change the stiffness. So in this way we can use the same machine tool for different purposes. For instance, higher cutting forces as well as smaller. And we tested in fact this system in an industrial environment in a company in Poland. So this is one. So if you want to keep cutting parameter optimized, you have to change the structure. So this jointry mount, also we can now change both the damping, so for dynamic and for static kinematics. But again, the problem is that this matrix component includes both kinematics and static, and we don't know how much is one and the other. So the other that we are doing here is changing only the static part, not kinematic.
Parce que le problème de l'usinage, c'est d'optimiser les paramètres de process et de minimiser l'erreur. C'est ça le problème. Pour minimiser l'erreur, donc on va minimiser les paramètres de process, surtout en IGV.
So now the question, what is meaning by optimization? What are the performance criteria? Is the optimization is about the increasing the productivity, reducing the cost, improving quality. The problem is that we are, if we go to education, we are teaching our students in production how to do faster, high volumes, but in times of crisis optimization is to adapt the production to the amount of work that we have. So, if you look on the parameter that can optimize, we optimize with respect to the cutting tooling machine. So these are mostly speed that is important, so it's for tool life. And this is not too much influencing directly the deviation because it's not affecting the force, but affects by two wear. So this is the part. But as regarding the new tool, it's not affecting the. So this is the main parameter that affect optimization. But with respect to optimization for productivity, so it can be compensated in some way. For instance, decreasing depth of cut, increasing, for instance, feed rates. Adaptive system for optimization, in my opinion, will not work because the most parts are complex parts. They don't have constant, for instance, either feed or depth of cut. So you cannot produce, say, 10 millimeter is one depth of cut and then change and have a stepwise system. So this works much also not good for practical application. So as optimization, it's a quite complex problem, and I don't think that we are having optimal system today. This is my opinion, yes.
Pour une machine donnée, un processus donné, connaissons avec ces techniques de mesure les déviations, donc la précision, la meilleure précision possible par la machine. Est-ce qu'il est envisagé de trouver une méthode de régulation à travers éventuellement faire d'autres efforts quelque part pour aboutir à avoir à la fin une sortie, une précision plus importante, même si le coût est important pour les usinages de très grande précision?
We know So we can now predict the deviation in the workpiece, but we cannot predict the precision of the machine tool, because as long as we cannot identify the source of errors, we cannot define a precision. But we know that this machine is capable to doing only, as with this cutting parameter, we can produce this part, but we cannot say how to do better.
Mais la précision, les déviations que vous avez obtenues, c'est à travers des mesures de force dans différentes directions. Mais on peut imaginer que si on voit la plus grande déviation, par exemple, on sait que son origine c'était telle force, d'essayer de trouver un système qui permet d'exercer une autre force contraire pour pouvoir, je parle bien pour des usinages de très grande précision, même si ça coûte.
We can with this method to locate the workpiece in the direction. We have calculated the workspace, the static stiffness and also kinematic. So at least theoretically we can place the workpiece in the position that gives the best say deformation, but we cannot active control the force.
Mais c'est envisageable ou pas?
Yeah, I think so. But theoretically, at least we can think that we can see now in which direction the forces are max, or the stiffness is minimum to adapt direction of forces. The problem is that it's very difficult to have at least at practical level some idea how forces direction will change during a complex form. But anyhow, we can generate any trajectory in fine corresponding, but as I say, we cannot say that we are now mastering the precision as long that we don't have idea how downward we can distribute the errors. Yes.
Je m'intéresse à la manière de fixer l'outil d'occupation avec les deux sphères.
The double?
Yes, the fixation.
No, but it's exactly fixed as the double, the normal double bar. So it has.
The contact.
So we are spherical contacts. So these are two balls there. Yes, yes. But I said that are compensated for deformation in both here and here. So I compensate Turner, but it's not any other. Unfortunately, I didn't bring with me this video that show exactly. So these are simple connections.
Simple contact.
Yes.
Second question. In the case of magnetic system tension of bearing, magnetic bearing, if we can simplify the relation between deformation and forces in the machine. Maybe simplification.
Also, I don't know, this is probably also more part of dynamics of the spindle.
En français, est-ce que le fait que dans une machine à usinage à très grande vitesse, par le palier électromagnétique, parce que là, le déplacement au niveau des paliers est le plus important.
Yeah,
Ce jeu, et on mesure directement le déplacement.
Yes, in high-speed machines it is important, the deformation and spindle nose, so there are centrifugal effect, but we didn't study this part. Now, as I said, so the model that we have today, it's corresponding to, say, a quasi-static way. So we are, so So depends also on the level of precision we discuss here. So for us, precision is a feature that today is not related to the scale of part. Can be very small or very large. The precision today should be the same because you have to, for instance, aerospace, you have a long wing, you have to produce the same precision because you have to reduce the weight, you have to reduce the thickness. So the precision should be the same as for instance, medical implants. So there should not be differences. So we applied this system also in Sweden in Saab, aerospacing, for measuring in, they have a machine with traverse of 40 meters for composite machining, so applied there, but also for accurate, for instance, machine from Switzerland, Micron, also which are working in high precision. So we measure with this system, for instance, in Volvo Aero. So this was the first result that confirmed with practical feelings of operator. So we measure in Volvo Aero 5 identical machines. So such 5-axis machine. And we have found out differences up to 60% between them. And it was exactly what the operator had the feeling. They said that, yes, we feel that this machine is not so good as the other. So we could also confirm this. So the system is efficient also for comparing different machinery tools. Because this is the most important part, also important part for user to know for some critical operation what will be the errors. So some operation like for instance drilling or milling with large face mills are very critical for the error. So this is a system that but of course there are more to develop also from dynamic point of view and also looking at high speed. So it's not a perfect system, but it's much efficient double for bar. So for us was important this concept elastically linked. Now we can develop other devices to make this link between the machining system and the part.
La méthode de mesure et action sur les axes de la machine en temps réel, peut-on utiliser cette méthode pour remonter justement au modèle d'imprécision, au modèle d'erreur de la machine? Parce qu'on peut agir mais mesurer en temps réel. Pendant l'usinage, pendant la fabrication, on peut mesurer directement que ce soit l'effort sur les axes de la machine ou les axes de l'outil, mais en même temps la mesure directe de la cote obtenue, en remontant par...
Measuring direct on the machine.
Yes. Measure and actuate. These techniques, I think we can discover real...
So we made some, as a problem is that, so you have two systems here. One is the two critical, one is the spindle, the other is guides here. And we don't have an absolute system, so if we can fix this to an absolute reference system to test only this, we can then, but the problem is that they are affected either both through the open loop and closed loop. So it's difficult if we could separate, so have here some reference system that you are testing only this, or reference system here too. but they are connecting each other through the open loop all the time. So it's difficult to distribute these parts. So, for instance, for many companies, they are interested. This was also this system thought as a system to test new machine before buying them. Also, Scania in Stockholm, they are buying for every year for 50 million crowns new machine tool, and they say that 70% of machine tools are not complying with ISO or even with the own regulation of the company. So it's a serious problem. So this was also, so many problems come not from speeder but from guideways. So this was also thought a method to say, okay, this is not only to say this guideways is good or not, but also to predict if in 1 month or 2 months or 1 year you'll be out of service. But as long as we cannot, so we are looking now for methods to separate these two parts. For instance, one method that we are looking is to generate, so if we can make a system that can relaunch this, so we can make just a transversal in the direction of guidewise and one perpendicular. So then we can separate the arrows. So we are looking also possibility to make such an allongeable system that can excite, also can make a trajectory in this direction, then perpendicular to guideways. So there can be solution, but they are not there yet.
So thank you. I ran out of memory, so
Yes, thank you. I can give you my phone. Collect our phones.
okay. We'll continue the
very
discussion
much.
after.
So I'll be next time here again, make another presentation.
If you want.
So I keep just going. Thank you very much for
Thank
your
you.
participation.
Thank you.
Thank you.